Hi, welcome to Fire Engineering Training Minutes. I'm Mike McEvoy, and in this episode I'm going to talk about using a device to measure exhaled carbon dioxide from a patient, referred to as waveform capnography. Capnography has long been present at the paramedic and advanced EMT level and is now included in the new EMS educational standards at the EMT basic level or EMT level and above. This device is an ALS monitor that also measures waveform capnography. Waveform capnography can be used on spontaneously breathing patients, like our patient here, or on patients who are being mechanically ventilated through an endotracheal tube or other advanced airway. We'll show you a picture of that later. Or it can be used on a patient who you're manually ventilating with a bag valve mask. We'll start with a spontaneously breathing patient. We're going to use a nasal cannula type device that's designed to trap exhaled air and to measure the end tidal or exhaled carbon dioxide from the patient. It has a normal nasal cannula that sits in the nose, loops around the ears, and this particular device also has a little mouthpiece that comes down and captures air that's exhaled out of the mouth. Now that the device is on the patient, we'll attach it to the monitor. When you plug it into the monitor, one of the keys to obtaining a good waveform from the patient's breathing is to be certain that the device is screwed into the port on the monitor properly. So it twists, and you want to twist it until you feel it firmly seated inside of the port on the monitor. Once it's attached, it will begin to show a waveform that actually is measuring the breathing rate of the patient and the carbon dioxide. And so what we're seeing here is a waveform that represents carbon dioxide that's coming out of the patient's mouth and nose. And there are two components to the waveform. One is the height of the waveform, which actually corresponds to the measured amount of carbon dioxide the patient is exhaling. And the other is the length of the waveform itself, which corresponds to the rate at which the patient is breathing. In this case, we see a rate displayed as 17 for breaths per minute, and we see 42 for the end tidal carbon dioxide. And normal carbon dioxide range in a healthy patient spans between 35 and 45 millimeters of mercury. If the patient was to breathe quickly, one of the things that we would see, we'll ask the patient to breathe rapidly. One of the things that we'll see in the waveform is that it will pick up its pace. As it picks up its pace, it also lowers the amount of carbon dioxide that the patient's exhaling with each breath, because he's eliminating carbon dioxide at a much faster rate. So we see a waveform that's much less high and faster across the screen. This is a classic hyperventilation situation. Now if we ask the patient to breathe slower, what we'll see on the waveform is a longer length waveform, and eventually this number 34 will start to increase to a higher value, representing more carbon dioxide being exhaled with each breath because the patient's retaining carbon dioxide. If the patient was to stop breathing, and we could ask our patient to hold his breath, what we'll notice is that this waveform will become a flat line. And after a certain period of time, depending on the device that you have connected, it will actually alarm. With this device that we're using here, we'll get that alarm after about 30 seconds of the patient not exchanging any air or not exhaling any carbon dioxide. That is a much faster response than you would see from pulse oximetry, which could take as long as 5 to 10 minutes to actually reflect a drop in oxygen in the patient. You'll see a change in 10 seconds when you're using exhaled carbon dioxide as a measurement of your patient's respiratory status. So the next piece that I would like to show you is what would happen to a patient if they were intubated and breathing through an advanced airway device. In a patient who's mechanically ventilated, the waveform capnography is a mandatory piece of equipment that should be in the line between the endotracheal tube in the patient and the bag valve mask. The device is an adapter that fits over the tube and then connects to the bag valve mask and measures the exhaled carbon dioxide through a side stream piece that actually draws the carbon dioxide into the monitor. Having the adapter in the tube between the bag valve mask and the tube itself allows us to see the waveform and tell whether the tube is actually in the trachea. One of the most common points for a tube to become dislodged is with patient movement. You notice that this patient has a cervical collar on, and most EMS systems require paramedics to place a cervical collar on any patient with an artificial airway to prevent the possibility of the tube being dislodged. That's not enough, however. It's mandatory to have monitoring continuously of the waveform to make sure that not only is the patient breathing, but that the tube is properly placed. This patient's breathing spontaneously, and you notice that I'm not squeezing the bag. He's able to draw air in and out of the tube directly through the bag and get 100% oxygen from the bag valve mask. There's no need, if the patient's breathing spontaneously, as we can see on the monitor, to actually deliver breaths to the individual. His end tidal capnography is 30. That's a little bit lower than a normal end tidal would be. If for some reason he was to stop breathing, we would notice that immediately by seeing the waveform flatten out, and after 30 seconds with this device we'll get an alarm that would tell us that the patient is no longer breathing. If the bag valve mask was disconnected, we could leave the monitor in place and the patient's end tidal and his respiratory rate would continue to be monitored by the adapter on the end of the airway. I'm Mike McEvoy. Thanks for watching.